the set 7 with the first exercise. Where we have here space shape. Shape can be described by the assemblage of mass. These masses are connected by massless rod. At time t equal to 0, the space shape is at rest and is right here with the mass 4 and the velocity v, which is given here the mass m, the distance here between the masses, let's say, or rod part, a, the velocity for the mass for the initial velocity for the mass 4 here v, represented by the vector v, and we know that the mass m1, m2, and m3 are given as following: m1 is 2m, m2, m3, and m4 are equal to the mass m. Asked is to determine the speeds we have seen in the lecture. There is 3 cases, which are the elastic impact, the partial impact, and the plastic impact. Okay, using now the formula which are given for the plastic impact. Before that, we have here to determine from the momentum of momentum, yeah, and after this we look that here the formula of momentum to determine using this method, that we can say, if I return back now to give the solution, one moment. Okay, what we know that here for the momentum, I write here exercise 1. We know that here for the impact, as after the impact, we have the momentum at the gravity center. The impact is equal to here B S after the impact. Then it means that we have the conservation of momentum, as we know that the general formulation is the sum of the forces to the momentum. But in our case, there is no external forces. Yeah, that it means here we have B dot should be equal to zero. And in this case, that it means it's the integration or the time integration that give that B is at the center weight is constant. Then it means that we can write that the momentum before the impact will be equal to the momentum after the impact. That now what we have here, we know that B, it's only the mass multiplied by the velocity. Here, what we have, if I return back now, here what we have before the impact, this is before, and here the representation after the impact. That is means here we have the mass M2, M3, and M1 are at rest, okay? And M4 has the velocity V, okay? When the impact happens, in this case, when the mass M4 struck the rods, in this case, we have one system which will rotate with certain angular velocity v dot. Okay. Then in this case, here the whole system, yeah, will have, or the whole masses will have the same angular velocity v dot, and then we can write that here b as here before, this will be here equal to M4 multiplied by V. Okay, and PS after the impact, this will be equal to M1 plus M2 plus M3 plus M4 multiplied by the velocity v, which is here in this case that v for the gravity center, as they have all the same velocity, not all the same velocity, but yeah, um, we'll consider the velocity of mass m1, of mass m2, m3, as well as the mass m4 after the impact. This is will be represented by the velocity of each mass, yeah, will be represented by Vs, and we look now after this, what is the velocity V1, V2, V3, and V4 after the impact, okay? Now, what I wrote here, this is in general, and there is here, if we take the coordinate system, in X direction, we have here Vs, it's only X dot S. In Y direction, we have here in Y direction, we have here Y dot S is equal to 0. Okay, there is only the here the velocity along X direction. And now if we look to the geometry of the problem, let's say, or of this system, what we have here, we have the gravity center or the centroid S, okay, where we have here the velocity, let's say, if I represented it here, let's say Vs, okay. Now what we have here X coordinate, Y coordinate. If we look now to the position respecting the XY coordinate system, the origin, we put it at the mass M1. Then we have here YS, okay, the position of the centroid, and we have here, it's given, the distance for M4 is 2A, okay, and for the distance of M2 and M3 is given here by 3A, okay. Now we develop further. What we have here, we can write that from this equation, let's say 1, okay, we can write that here M for one moment. It's coming. We can write here now this relation that mv4, which is the impact, or let's say momentum, before, and here after we make the equality between the two terms here, then we get m4 v will be equal to m1 plus m2 plus m3 plus m4 multiplied by here Vs. Then it means here we can write that Vs, which is only x dot, this is will be equal to m4 divided by m1 plus m2 plus m3 plus m4. And this multiplied by the velocity v. Okay, as we know that here the mass m1 is equal to 2m, and the mass m2, m3, and m4 are equal to m. Then we replace, we will get here that Bs will be equal to 1 divided by 5 v. Okay, this is what we get now. Now, if we look to the expression, okay, we have the velocity at the center. Then we can get from the expression of the velocity for different points, let's say, we know that here the expression, for example, VE I write here from kinematic, we have here the velocity, for example, at any point E is equal to velocity of the point, for example, B plus omega cross R B E. This is the general formulation what we have seen, for example, between the velocity of any point can be considered, yeah, or can be determined by considering the velocity of the point, yeah, and to shift this velocity, there is the relative velocity here, omega cross R BA. Now, if we apply this, then it means here we have the velocity V1 okay, of the mass M1. I write it here for simply only simplification of notation. V1 is the velocity of the center width Vs plus omega cross r, the distance between the center width, yeah, and the mass M1. Okay, now we have also this is equivalently we have also V2 it's also Vs, the same equation, plus omega cross Rs2. Okay, Rs1 and Rs2 are equivalently to the vector position here, RBE. Here, the distance between the center width and the mass M1. The same here is the distance or vector position, yeah, um, from the center width S and the mass M2. And this is also is the same, yeah, for all, let's say, um, position here are, um, let's say, RS4 and so on, yeah, for the mass M3 and M4. Now, if we look to the position, we have RS1 will be the position here, 0 minus ys, and in z direction it's 0. Okay, we have the same for rs2. This is will be here equal to minus a 3a minus ys and 0. Okay, now you look to the, we look for example here to the geometry. If we take for example M1, yeah, has only its 0 in x direction, yeah, the position, and in y direction it's only minus ys. Okay, if I take M2, yeah, the same principle. In x direction it's minus a, okay, in y direction it's 3a, okay, and of course in z all components of z direction of all masses, yeah, are equal to 0. Now if we take for example m3 will be x, in x direction it's a, okay, in y direction 3a, yeah. M4 will be in x direction 0, and in y direction is this distance 2a. Okay, now I return back to the solution. Then it means here we take here RS3, this is will be equal here to A 3A minus YS and 0 and RS4 will be equal to 0 2A minus YS and 0. These are the vector position of all masses from mass M1 until M4. Now, if we take this description that we have only to determine now the position of YS, that is means, yeah, we have to look and compare it to the origin, yeah, of the coordinate system. What is YS? We know from the formula, yeah, that YS if we take it, we know that it's only the sum of mi, yi divided by the sum of mi. Okay, where I is vary from 1 to 4, we have 4 masses. Okay, then we get here, if we develop, that is means we have m1 with 0, y1 plus m2 multiplied by 3a plus m3 multiplied by 3a and plus m4 multiplied by 2a. And this all divided by m1 plus m2 plus m3 plus m4. Then this will give 8 divided by 5a. Okay, this is now the position, the position in y direction, in x direction is equal to 0 of the center weight. Now, as m4, m3, m2, and m1 are given as function of the mass m, okay, then we get here 8 divided by 5e. Now, if we look here to the expression of the velocity Vs, we have now, we said V1 is Vs, okay, Vs is given here by 1 divided by 5V, yeah, and we have here omega, it's only phi dot, okay, and RSA, it's here if we replace that, it means has component RSE, sorry, are given by this expression 0 minus ys0. Ys it's given by the following relation or by the value which is 8 divided by 5a. Okay, we have only now to replace in this relation for the velocity v1, v2, v3, and v4. Then it means we will get here now v1 is equal now here we have 1 divided by 5 v, and we have here in y direction it's 0 and 0, and here plus omega cross here. Now we have omega, it's given in z direction, yeah. And for the r as 1, then we have here 0 minus ys 0. Then it means we have here 0 minus, that means we have here minus 8 divided by 5 and a 0. Okay, then we have only to make the cross product. Then we get here, this is will be 1 divided by 5 multiplied by v plus 8 divided by 5 a phi dot. And this is given in x direction. Okay, now this is the absolute value of the velocity or the amplitude. And now if we develop further, we have here V2 will be equal to 1 divided by 5 V minus 7 divided by 5 A phi dot in x direction minus A divided by multiplied by phi dot in y direction, and here 0. Okay. Now, if we look to V3, the same principle. If we develop, we will get 1 divided by 5 V minus 7 divided by 5 A phi dot in y direction. It's A phi dot and 0 in z direction. Now we take V4 This will gives here 1 divided by 5 v minus 2 divided by 5 a v dot and other components are equal to 0. Then it means now here we have the all velocity from of the mass m1 to m4. Okay, now the value of v, yeah, or let's say the v, the initial velocity of the mass m4, it's given, yeah. A also it's given, yeah. The problem is v dot, it's not given. Okay, that completely to solve the problem, we have to determine now v dot. Okay, this is we can use, okay, what we call the momentum of the momentum. Then it means we have here L, what we noted in the lecture, yeah, here determination of v dot. Okay, here it's unknown, yeah. For that we use the momentum of the momentum, and as I said, we note it in the lecture by L, okay, and this is here I write LS, okay, let's say relative, yeah, which is in our case here the sum for I equal to 1. Okay, this is in general case. To n, it's R of the center with S. Let's say I wrote it by relative, cross M I cross VI. Okay, this is what we defined in the lecture, and this is will be considered as constant. Okay, now if we do this, then we get here LS here relative, and this is before the impact. This is will be equal to R S 4 as only the mass 4 before the impact, only the mass 4, and 4 has velocity. Then it means here cross m4 multiplied by the velocity v. Okay, then if we develop here, we will get as rs4, it's given here, okay, by the following component in x, y, and z direction. Okay, v, it's given only in x direction, yeah, and we have m4, which is equal to m. Then it means if we develop further, then we get here minus 2 divided by 5 m multiplied by a multiplied by v, and this is given in z direction. Okay. Now the momentum has only one component, which is given in z direction. Yeah, other components are equal to 0. Now, if we take the L, the momentum of the momentum here, Ls relative, okay, and this is after the impact. This will gives here then we have here R R S1 cross M1 V1 plus R S2 cross M2 V2 plus R S3 cross M3 VS3 plus R S4 of the mass position of the mass 4 cross the mass M4 and the velocity S4. Now, if we develop further, yeah, we're on place now here, RS1 to RS4, okay, by we have the position, vector position of the masses, mass M1 to mass M4, okay, this is are given here by the following component, as well as the velocity, yeah, V1 until V4, okay? Then we have only to replace this, okay? Then we get here, okay, I will make it more in details, yeah. R, that for U, R, S1, cross, M1, cross M1, sorry, V1 or VS1. It's not important the notation. This is will give here 0, 8 divided by 5 with minus sign multiplied by E and 0. Cross M1, okay, and we have for VS1 or V1, it's 1 divided by 5 multiplied by V plus 8 divided by 5 A phi dot. And here we have 0 and 0. Okay, then if we develop, we will get here 8 divided by 5 A M1 multiplied by 1 divided by 5 V plus 8 divided by 5 A phi dot in Z direction. This is now the expression of this term here. Yeah. Now we take the second term, okay, corresponding to the mass M2. Then we have here R S2 cross M2 V2. This is will be equal to minus A 7 divided by 5 A and 0. And here also we cross M2 1 divided by 5 for the velocity V2, V minus 7 divided by 5 A phi dot minus A phi dot and 0. And this will give here the expression of this cross product A square M2 phi dot minus 7 divided by 5 A M2 multiplied by 1 divided by 5 V minus 7 divided by 5 A A phi dot. This is also, it's given in Z direction. Okay, now if we look to third product, R S3 cross M3 V3. Okay, this, yeah, we will find, yeah, as time is running. Now we use the same procedure, yeah, as for RS1 cross M1 V1, also RS2 cross M2 V2. That is means we have the component of RS1, the vector position, yeah, of the mass M1. We have the velocity as function of V dot for the velocity of the mass 1 and the mass 2. Okay, we have only to make the cross product, and if we do so, then we will get here A2 A square M3 phi dot minus 7 divided by 5 A M3 multiplied by 1 divided by 5 V minus 7 divided by 5 A phi dot. And this is given also in Z direction. The same principle for the mass M4. Here we make the cross product also, and we will find minus 2 divided by 5 A M4 1 divided by 5 V minus 2 divided by 5 A phi dot. And this is also in Z direction. Then if we develop now further, okay, we have all expression here, the fourth terms of the momentum of momentum, okay? This is after the impact, and we have the expression here before the impact, okay? Then we make the equality between this term here and this term, okay? Where all terms here are given by the following relation here. If we develop, we will get here now LS relative here before, okay, will be equal to LS rel after. Then it means we will get here, if we replace, we will have minus 2 times 2 divided by 5, A and V. This is will be equal to 56 divided by 5 A square and phi dot. Then it means we have now phi dot will be equal to minus 1 over 28, okay, V divided by E. Now, this is the expression of the angular velocity, okay, as I said, which is unknown, yeah, and the velocity V1 to V4, okay. Now we have only to replace phi dot by its value, yeah, and we get here, yeah, let's say V1 will be equal 1 divided by 7 V, okay, and V2 will be 1 divided by 4 V, 1 divided by 28 V, and 0. Then it means here, if we have to determine the magnitude V2, okay, here it's only the magnitude of V2, and this will give here the value of 0.253 V. Okay, this is the value of the velocity V2. Okay, the same principle, yeah, we use it for V3 and V4. Okay, I have finished with the exercise 1. Yeah, I will go to the exercise 2. And in this exercise 2, we have the ball M, which is here is shout out of the apparature here of mass capital letter M, and there be reached the relative velocity V0. Okay, at time t equal to 0, the apparature is at rest, and the spring here with the coefficient C is here unstretched. The ball is directed, yeah, at an angle alpha relative to the apparature with the mass M. then we say that the apparature here moves without friction. That is means there is only the contact, the normal contact force, we note it here by A, or let's say the reactions of the ground on the mass M. Given the mass of the apparature, the mass of the ball, yeah, the coefficient C, here the angle alpha, as well as the reached relative velocity V0. We have to determine the speed V1 of the apparature when it moves, yeah, due to the, let's say, the shut out. Then it means there is velocity of the apparature. Of course, it's different from the velocity of the mass of the ball. The speed V2 of the ball, yeah, the integral here of this normal force A and the path xt here of the mass capital letter M or of the apparature. Now coming to the solution, what we have here, if we look to the which forces are acting on the system, one moment. Then if we look to the here the system apparature with the mass M, then we have here the contact force or the normal force A. Okay. Now when the reaches certain velocity, initial velocity V0, okay, due to the motion, there will be the velocity V2 of the mass of the ball M. Okay, there is no friction, mu is equal to 0, and the apparatures, yeah, will move with, yeah, the velocity v1. Okay, and we take this coordinate system x and y. That is means v1 has component only in x direction, and v2 as well as v0, okay, have component in x as well as in y direction. Now coming to the solution, okay, we have here exercise 2. Now, if we look to the, uh, let's say, the impulse or um, uh, to the momentum, what we have, if we look to the, let's say, different velocity. That's what we have. We have here the momentum, we have the mass V2, sorry, the mass multiplied by V2 in x direction here minus m multiplied by V1. Okay, this is here after the, let's say, the shutting out, and this will give here minus 0. This will give here equal to 0. Okay, now if we look to this expression, we will get here V1. It's only the mass of the ball divided by the mass of the apparature multiplied by V2x. Okay, now if we look here that the velocity, okay, what we have the velocity V2, okay, which is the absolute velocity. It's equal to V1 of the apparature, which is the frame velocity, plus the velocity of the mass m, which is the relative one. Okay, then this is equivalently to say that always we have the absolute velocity is always decomposed into two terms, the frame one, okay, and the relative one. In our case here, the frame one is the V1 and the relative one is the V0. Okay, now this is here, this expression here coming from what we have seen in the lecture, that the integral from 0 to T1, okay, of the sum of the four applied forces F dt. This is here is equal to the m, which correspond to b dot v1, here mv at time t1, okay, minus m velocity at time here at time t0. Okay, this is, it's only b dot 1 at time t1, and this is b dot um, at time t0, the initial one. Okay, the initial one here is 0, and at time t1 we have the velocity of the mass small m and the velocity of the mass m. Now, if we look to the component of the velocity here, what we have for this term here, the absolute velocity, what we have here V1, which is negative, okay, opposite direction to x, and we have V0. okay, as vector. Now what we get the sum of V1 and V0. We have here the absolute one, V2. Okay, that's where there is here the angle alpha between V1 and V0. Now if we take V2, V2 will have component in x direction as well as in y direction. That it means we have here, let's say, V2 x, and we have here V2 y. Okay. Now, if we look to this, that we can write here from this component here, V2x, that is means this one here. If we write this, we can get here this will give V2x will be equal to V0x minus V1. Okay. Sorry, I make a mistake here. The direction, only the direction of V1, it's not negative, that is here. This is now V2, and here we have V2x. Okay. Now, if we take this, that is means here we have V0x minus V1. Okay. And now, if we develop further, then we have here V0x. Okay. When we decompose it, it's only V0 cosine alpha. Okay. Now we get here, this is will be equal to V0 cosine alpha minus V1. Now, from this expression here of V1 as function of V2x, okay, this is I write it by equation 1, okay, and here equation 2, then 2 in 1, I get here V1, it's the mass m divided by m plus capital letter M V0 cosine alpha. And this is the expression of the velocity of the apparature. Okay, all terms here, yeah, are given, yeah, in the exercises. Now, if we look to the V2 of the mass M2, yeah, after the shot, then the second questions, yeah, to determine V2, then we get here, we have here V2x, okay, we're on place now V1, but its expression here, that it means we have here the mass, small letter m of the ball divided by m plus capital letter M V0 cosine alpha, and this is equal to small m divided by capital letter M V2 x. Then it means we get here V2x will be m divided by small letter m plus capital letter M V0 cosine alpha. Okay, this is one. It's only the component of V2 here in x direction. In y direction, we have, this is, I write it by A, B, we have V2 in y direction is equal to V0 in y direction, and this is will be V0 sine alpha as V1, this is the relative one, as this is the relative one in y direction. V1 has only one component, the frame one is given in x direction. There is no component in y direction. That it means the absolute velocity V2 has in y direction only the relative one. Then it means here we can get that the V2, okay, absolute, which is equal to V2 here, the magnitude, and this will give here the square root of this term, yeah, square plus this term square. And this will give here m divided by m plus capital letter M cosine alpha square plus sine alpha, and here all multiplied by V0. Okay, this is the expression of, let's say, the velocity V2. Now coming to the third part, yeah, it's asking the integral of E dt. Now what we have, if we take now the impulse in y direction instead to use in x direction, as we know, yeah, from this expression here, this one, we know that the sum of the integral of the forces, yeah, in y, the sum, the integral of the forces from the initial time to the an arbitrary time of the external forces dt will be only the difference, yeah, of b dot. That is means m v at time t1 minus mv at time t0. We use this formula here. Okay, to calculate the integral of the contact force. Now what we have here, um, v at time t1 minus mv at time t0, and this is will be equal to the integral of a dt. Okay, now what we have here, mvt1, it's only the mass multiplied by v2 in y direction, and this is minus 0, and here equal to the integral of a dt. Then it means here we get the integral of a dt will be equal to the mass multiplied by v0 sine alpha. This is the expression now of the integral, yeah, with respect to time of the reaction A between the ground and the, let's say, uh, the aperture or the mass, capital letter M. Now what it asked for the fourth questions here to determine x t, yeah, of the mass of the mass M. Okay. Now what we have here, we can apply now, yeah, um, to get this. That is means we will get the differential equation. Okay. What we have here, we look to the force. If we apply the Newton law, if we apply now the Newton law for, or we can apply also D'Alembert um, uh, principle, we have our aperture with a mass, capital letter M. This is will move, yeah, with position x, velocity x dot, and the acceleration x dot dot. Which forces are acting on the system? If we make here the cut, okay, the free body diagram, in this case, we will get only the force um, uh, in the spring. That is means we have only the spring force here. We note it by FFA, and this is C multiplied by X. Okay, then it means now if we make the equilibrium with the Newton law, yeah, we make here Newton in X direction. What we have here as external forces, we have minus c multiplied by x, which is equal to the mass m x dot dot. Okay, then it means we have got here x dot dot plus c divided by m multiplied by x, and this is will be equal to 0. This is the differential equation of motion, okay? And this is here, this term is only omega square, okay? Then it means here what we have the x dot dot plus omega square x is equal to 0, yeah? Where here omega is square root of c divided by n. Okay, now the solution, we have already seen it, yeah, in different example. We can write, yeah, the solution of it. We have x, it's b or a, or it's up to you, yeah. It's not important, the notation, let's say, but it's the important, it's the solution which is one known as function of sine, yeah, plus here c cosine omega t. Okay, now as we have done it before, we have to make only the time derivative. Then we have here x dot, which is equal to omega b cosine omega t minus c or omega c sine omega t. That's what we know to determine b and c. It's always the same procedure. Yeah, we have to determine b and c. Okay, then we have from the initial condition, what we have here, we have xt at time t equal to 0. There is no displacement, yeah, for the aperture, that we have x at time t equal to 0. This is equal to 0. That it means here we have c, which is equal to 0. Now x dot the velocity at time t equals to 0, this is equal to minus v1. Then it means here we have omega multiplied by b. This is will be equal to minus v1. Then it means here we have b, which is equal to minus v1 divided by omega. Then it means here we are on place now c and b, yeah, in the expression of x, yeah, of the solution of the differential equation here, yeah. Then we get here now x at time t. This is will be equal to minus v1 divided by omega sine omega t. This is the solution, and where we know the value of v1, that is minus m v0 cosine alpha divided by omega multiplied by m of the ball plus the